Imagine sending a message across the universe in an instant. What would it be like to have information travel faster than light? This isn't science fiction. It's a question that's puzzled scientists for decades. Today we'll explore a strange and exciting area of science: quantum entanglement. We'll journey into the heart of atoms. We'll uncover the secrets of particles linked across vast distances, and we'll examine the implications for the future of communication. Get ready for a mind-bending adventure as we explore the potential for information to travel faster than the speed of light. Fasten your seatbelts, science fans, because things are about to get strange. Quantum entanglement is a bizarre phenomenon in the quantum world. It links two particles in a profound way. Imagine two particles born at the same moment. They are connected. What happens to one instantly affects the other, even if they are light years apart. This connection, this entanglement, is at the heart of our exploration. How do these particles communicate? Is it faster than light? These are questions that have challenged physicists for generations. Join me as we dive deep into the mystery of quantum entanglement. We will explore how it works, the experiments that have stunned the scientific community, and what it means for our understanding of the universe. Imagine two dancers, perfectly in sync. They move as one, their steps mirroring each other. Now imagine those dancers are tiny particles, linked by an invisible force. This is the essence of quantum entanglement. Two particles, once connected, become entangled. They share a special bond, a shared state of existence. Even when separated by vast distances, they remain connected. If we observe the state of one particle, we instantly know the state of the other, no matter how far apart they are. Think of it like this. Imagine flipping two coins. If one lands on heads, you know the other must land on tails. It's not magic. It's a fundamental principle of how these entangled particles work. But in the quantum world, it's even stranger. The particles don't have a definite state until we observe them. Albert Einstein famously called quantum entanglement spooky action at a distance. He was troubled by the idea of particles influencing each other instantaneously across vast distances. It seemed to violate one of the fundamental principles of physics, that nothing can travel faster than light. Einstein believed there must be some hidden variable, some unknown force, explaining this strange connection. But experiments have consistently shown that quantum entanglement is real, and that the communication between entangled particles is instantaneous. This spooky action has profound implications. If we can harness the power of quantum entanglement, we might be able to create new technologies that defy our current understanding of communication and information transfer. The idea of information traveling faster than light is intriguing. It could revolutionize communication, allowing us to send messages across the universe in an instant. But can quantum entanglement really be used to send information? This is where things get even more complex. While entangled particles are undeniably connected and their states are correlated, it's not clear if we can use this connection to send information faster than light. The act of measuring one particle seems to randomly determine the state of both particles, making it difficult to control or encode information. The challenge for scientists is to find a way to manipulate these entangled particles and use them to transmit information in a controlled and meaningful way. If we can overcome this hurdle, the possibilities are limitless. Let's delve deeper into the heart of this mystery. Imagine two entangled particles separated by a vast cosmic expanse, perhaps even light years apart. They are connected, linked in a way that defies our everyday intuition. Think of them as two spinning coins, flipped at the same time. But instead of landing on heads or tails, these particles exist in a blurry state of possibilities. They are both heads and tails simultaneously until we observe them. Now, the moment we measure the state of one particle, something extraordinary happens. The act of observation forces it to choose a state heads or tails. And here's the mind-blowing part. At that very instant, the other entangled particle, billions of miles away, instantly snaps into the opposite state. How can two particles separated by such immense distances influence each other instantaneously? It's as if they have an invisible thread connecting them, a thread that transcends the limitations of space and time as we know it. This thread, this connection, is what has puzzled scientists for decades. It challenges our fundamental understanding of how information travels in the universe. After all, Einstein's theory of relativity tells us that nothing, not even information, can travel faster than the speed of light. So, how do entangled particles communicate? Do they send signals faster than light, breaking the cosmic speed limit? Or is there something more profound at play, something that rewrites our understanding of the fabric of reality itself? Measuring an entangled particle is crucial in quantum physics. It forces the particle to choose a state. This choice instantly affects its entangled partner. Imagine two boxes with colored balls. Opening one box reveals the color in the other, even miles away. Similarly, measuring one particle reveals the state of its partner. The illusion of instantaneous communication. But does this mean that information is actually traveling faster than light? Not necessarily. The strange correlations between entangled particles don't seem to allow for the transmission of information in the traditional sense. While the connection between entangled particles is instantaneous, the outcome of measuring one particle is random. We can't control the state that a particle will collapse into when we measure it, making it impossible to send a specific message or signal. The information we gain from measuring one particle is random, and while it tells us something about the other particle's state, it doesn't allow us to send a targeted message. It's as if the entangled particles are sharing a secret language, but we haven't cracked the code yet. How do two particles become entangled in the first place? It often occurs when they interact with each other in a specific way, usually at the moment of their creation. Imagine two photons, tiny packets of light born from a single atom at the same moment. These photons, linked by their shared origin, emerge from this atomic event in an entangled state. They are like two sides of the same coin, forever linked by their past. Other processes can also lead to entanglement. Scientists can entangle particles by passing them through special crystals or by manipulating them with lasers. The exact methods may vary, but the underlying principle remains the same, creating a strong correlation between the particles' states. Once entangled, these particles cease to exist as independent entities. They become part of a single unified system even when separated by vast distances. It's as if they share a single existence spread out across space. Imagine two waves on the ocean created by the same disturbance. These waves, though physically separate, are part of the same underlying wave function. Similarly, entangled particles are described by a single wave function that encompasses both of their states. This shared existence has profound implications. It means that the properties of entangled particles are no longer independent but are correlated in a way that defies classical physics. One of the most common ways to entangle photons is through their polarization. Polarization refers to the direction in which a light wave oscillates. Imagine a wave on a string moving up and down. That's one polarization. Now imagine the wave moving side to side. That's another polarization. Photons can be polarized in different directions. When two photons are entangled through their polarization states become correlated. For example, if we measure one photon and find it to be horizontally polarized, we instantly know that its entangled partner is vertically polarized. This correlation in polarization states is one of the most striking examples of quantum entanglement, demonstrating how the properties of entangled particles are intertwined. The strange correlations between entangled particles have led some to speculate that they could be used for faster-than-light communication. Imagine sending a message instantaneously to a distant star system. The possibilities are mind-boggling. However, as we've explored earlier, the randomness of quantum measurements makes it incredibly challenging to use entanglement for controlled communication. We can't force entangled particles to collapse into a specific state when measured, which means we can't encode information onto one particle and have it reliably transmitted to the other. Despite these challenges, research into quantum entanglement continues to push the boundaries of our understanding. Scientists are actively exploring ways to manipulate and control entangled particles, searching for potential loopholes that could lead to groundbreaking applications. Quantum entanglement is a testament to the interconnectedness of the universe at the most fundamental level. It reveals a strange and beautiful reality where particles are linked across vast distances, their fates intertwined in ways we are only beginning to comprehend. While we may not be sending messages faster than light just yet, the study of entanglement has opened up new avenues of research in quantum computing, cryptography, and our understanding of the universe's fundamental nature. The journey into the heart of quantum entanglement is far from over. It's a journey that continues to challenge our intuitions, spark our imaginations, and push the boundaries of human knowledge. For decades, quantum entanglement remained a theoretical curiosity, a mind-boggling prediction of quantum mechanics. But scientists are a tenacious bunch, always seeking concrete evidence to support even the most outlandish ideas. The challenge was clear: design an experiment that could definitively prove that the correlations observed between entangled particles were not due to some hidden classical mechanism. They needed to rule out any possibility of secret signals traveling at the speed of light or slower. This quest for proof led to a series of increasingly sophisticated experiments, each designed to close loopholes and address potential objections raised by skeptics. The goal was to establish beyond any reasonable doubt that quantum entanglement was indeed as spooky as it sounded. One by one, scientists devised ingenious ways to eliminate potential loopholes in their experiments. They increased the distances between entangled particles, ensuring that even light wouldn't have enough time to travel between them during the experiment. They developed methods to randomly choose the measurements performed on each particle, ensuring that the choice of measurement on one side couldn't influence the outcome on the other. Every loophole closed brought them one step closer to proving the undeniable reality of this bizarre quantum phenomenon. These experiments were like a high-stakes game of chess between scientists and nature, with each move carefully planned and executed to outmaneuver the universe's attempts to hide its secrets. And slowly but surely, the evidence began to mount, pointing towards the inescapable conclusion that quantum entanglement was real. The groundbreaking experiments that finally convinced the scientific community were a testament to human ingenuity. Pairs of entangled photons were sent to different locations, sometimes kilometers apart, and their polarizations were measured independently. The results were astounding. Despite the distance and the random choice of measurements, the correlations between the entangled photons persisted. Their states were intertwined in a way that defied classical explanations. The communication, if you could call it that, seemed to be instantaneous, as if the particles were linked by an invisible thread that transcended space and time. While these experiments didn't allow for the transmission of information faster than light, they provided the most compelling evidence yet that the connection between entangled particles was real, and that it operated outside the bounds of classical physics. The implications of quantum entanglement are far-reaching, extending far beyond the realm of theoretical physics. While the dream of faster-than-light communication may remain elusive for now, entanglement has opened up exciting new possibilities in other areas. Quantum computers, for example, leverage the power of entanglement to perform calculations that would be impossible for even the most powerful classical computers. Quantum cryptography promises secure communication channels that are theoretically impossible to eavesdrop on. And as we delve deeper into the mysteries of entanglement, we may uncover even more profound implications, potentially revolutionizing our understanding of the universe and our place within it. The future is entangled, and it's a future full of wonder, possibility, and perhaps even a touch of spookiness. Quantum entanglement stands as one of the most baffling yet promising areas of scientific exploration. It challenges our understanding of the universe, suggesting a reality stranger and more interconnected than we ever imagined. Quantum computing and cryptography are being reshaped by our growing knowledge of entanglement. As we delve deeper into the quantum realm, who knows what other discoveries await? Be sure to like, subscribe, and hit that notification bell for more adventures.